Hello, welcome for joining today's SZ4D Modeling Collaboratory Volcanic Systems webinar. On your screen, you will see a brief summary of the SZ4D Science Community Initiative, as well as the Modeling Collaboratory for Subduction Research Collaboration Network, which is what these webinars are part of. The theme this week is magma storage, and today's speakers are Emilie Hooft and Chris Huber. Carl Anderson and I are the hosts. Panabendu Moitra and Penny Wieser are moderators, and Philip Ruprecht and Mark Iorso are speakers from last Tuesday. This is your panel. I would like to draw your attention to the planning meeting. We are scheduled for tomorrow from 12 noon to 2:30 Central Time. The purpose of the planning meeting is to build upon these webinars and define a vision for a potential future modeling collaboratory. What we are planning to do on Friday is to identify some science priorities and discuss and outline, a potential vision, sort of the nuts and bolts of how a modeling collaboratory or volcanic systems component of a modeling collaboratory could facilitate, could help achieve those science goals. So if you are interested in participating, interested in trying to shape a vision for a modeling collaboratory, please join us on Friday. If you're interested but you're unable to join on Friday, the report for this volcanic systems workshop, the series of webinars and planning meetings, the report as work in progress is available on the MCS website. This is a screenshot, and there is also the asynchronous feedback form where you can enter questions, comments, any feedback that you would like us to take into consideration in our discussions, in the planning, in the report. With that, I will give it to Kyle, who will introduce our first speaker.
Great, thank you, Hoga. So our first speaker today is Emilie Hooft. Emilie earned her PhD in marine geophysics jointly from MIT and Woods Hole on mid-ocean ridge systems. Emilie was a postdoc at the Carnegie Institution before moving to the University of Oregon, where she's now an associate professor. Emilie studies magma transport and the interaction of mantle plumes with ocean ridges. She's led expeditions to Cascadia, oceanic sprouting centers, and volcanic hotspots, where she collects dense geophysical data for use in inverse modeling. Emilie has also worked to develop advanced seismic methods for studying these problems. Today, she will be discussing magma storage from a geophysical perspective. Emilie?
Thank you, Kyle. I'm excited to share my work with you today. And there, is that working? Thank you. I'm going to talk about magma storage from a geophysical perspective and try and talk a little bit about geophysical data and how it relates to modeling. Oops. All right. Okay, so some of the questions we can ask about magma storage is what are the size and depths of magma storage regions? And what are the melt fractions and what's the distribution of melt within these different areas of the magmatic system? What are the connections between magma storage regions? And all those questions are important for how the thermal, chemical, gas evolution of the magma happens, and also how magma systems become pressurized and lead to eruptions at the surface. And one of the questions we can ask is, how could you geophysically test the currently envisioned transcrustal magma plumbing systems? And this is a conceptual diagram of a transcrustal magma plumbing system, right? And so in terms of a modeling collaboratory, we can also ask, how do you actually build a system, this kind of conceptual system, in a consistent physical and chemical manner? And here is a different attempt from a thermal model to explain that. And so what I'm going to talk about today is talk a little bit about what we understand and what's surprising about things that we've found. I'm going to talk at most length about what we do not understand and some areas for progress, and then finish by talking about how our geophysical observations and models interact, and really that's going to lead into Chris Huber's talk, who's going to talk much more extensively about that aspect. So what we know is that there are shallow, low velocity bodies under volcanoes, and these often, but not always, match geodetically and petrologically inferred magma storage regions. And that in some areas that are particularly volcanically active, we've imaged large mid or lower crustal magma storage volumes, but that in general, the mid or lower crust has been more difficult to really understand the structure of. And I'd also like to really point out that mid-ocean ridges have really shaped our models and our concept of a mush-dominated magma system with the overlying higher melt fraction sills, right? And so in a mid-ocean ridge system, that sill lies at the top. In this cartoon, it's somewhere sort of in the middle of the mush in the upper crust. And so I'm really going to cover some of these observations with an emphasis on what's surprising in the next couple of slides. So this is a rendering of a P-wave seismic tomography result from Newberry Volcano in the Cascades. So the graphic rendering shows the magmatic volume inferred from this study as this red object. It's a low velocity volume at about 3 to 5 kilometers depth. And that entire volume contains about 2.5 to 8 kilometers cubed of melt. The other reason this image is nice is it shows in gray that this low velocity volume is surrounded by relatively high velocities that we infer to be cooled intrusives. So that's an interesting observation, that the remnants of this magmatic system are present around it. Okay, and so similar results in terms of a shallow magmatic system have been found at Santorini Volcano. And this is another 3D rendering that I'll show you of that system, where the low velocities, the most pronounced low velocities, are in red. Other shallower low velocities are in gray, are inferred to be more porous rocks, and then in yellow is a more mush-like region. And so the low velocity volume itself is at similar depths, 3 to 6 kilometers. The entire volume of the low velocity is about 35 kilometers cubed. And from the seismic velocity reduction, we can infer about 4 to 13% melt, or this region could be fully molten. So one of the things I want to emphasize in this talk is that the results from seismic tomography or different studies, really, there's a family of models that are consistent with those observations. And just because this is my favorite image doesn't mean it's the real structure in the Earth. And so there's at least 2.2 kilometers cubed of melt, and this really is a minimum boundary, and I'll emphasize this more in a minute. One interesting thing is that even the volume of melt within this low velocity body is much larger, 10 to 100 times bigger than an intrusion that occurred at Santorini about a decade ago. It didn't lead to an eruption, but there was a very strong geodetic and seismic unrest. The other interesting thing, okay, and so this star shows that geodetic intrusion occurred exactly within this low velocity volume. Then these arrows show that Santorini sits in a very strong regional extension, and that regional extension is dominating or is controlling this mush that extends off to the northeast from the volcanic area. So one of the other interesting observations is that magma chambers can be offset from the main volume. And this is a rather busy figure from Lerner et al. On the left, it shows Mount St. Helens with, in this case, in pink, the geodetically inferred magmatic volume is not at the same location as the seismically inferred magma system. And the seismically inferred magma system is offset, outside of what you would call the bounds of the edifice from the surface topography. And so the figure on the right is a compilation from the literature of many different observations, geodetic and seismic, and the colors show different kinds of volcanoes. And the point here is that a relatively large fraction of volcanoes have magmatic systems that appear to be offset. So this suggests that tectonics and local geology matter. An interesting observation from this study was also that as the volcanic system becomes more voluminous and productive, which are the bigger symbols, or when it becomes a more morphologically more well-established, like systems that have a caldera, which are the black symbols, the system tends to become more centralized. So that indicates that there's like a crustal maturation during the growth of volcanoes. This is a nice result from a mid-ocean ridge study at the Endeavour segment of the Juan de Fuca Ridge. And on the right, you can see cartoons showing that these mid-ocean ridge systems are mush dominated. Those are the lighter beige colors. And then the system is topped by a magma lens, the red at the top here. And so it seems that melt is accumulating against some boundary. The images on the left show here the organization of melt inferred from low velocities in the uppermost mantle, and then the organization of melt at crustal depths within this crustal magmatic system. And so as the cartoons on the right also show, melt in the mantle is much more broadly distributed over a wider region. And it has a different orientation than melt within the crust. So there's, again, a rheological control on how is melt being shaped and organized as it moves through these different layers within the lithosphere. The other interesting feature is that the sides of these magmatic systems are very steep. So you can see that on the right-hand side. And shown in blue arrows is hydrothermal cooling paths that are inferred from this velocity and therefore thermal structure. And this indicates a really strong role for convective heat removal in the crust in shaping the rheology and the shape of the magmatic system itself. So to summarize, low velocity bodies are often surrounded by high velocities. They're small, but in fact, they're 10 to 100 times larger than the volume of typical intrusions. Magma storage systems in the crust are often offset, and there's an influence of local tectonic or geologic structures, but also an indication that as the crust matures, the systems become more centralized. And Lastly, I made the point that hydrothermal cooling shapes magma systems, and that the thermal structure and the rheology of the lithosphere is really important in controlling magma accumulation. So now I'm going to move on to what we do not understand. And I'm going to talk about this in 3 sections. One is really exploring more, what are the actual velocity values in low velocity regions and the limitations and directions we can move for actually resolving magmatic areas. What are the melt fractions that we can infer in these regions, and how can we advance in that area? And then this question of how do we better probe and understand the structures in the mid and lower crust beneath volcanoes. So to start by talking about actual velocity values, I'm going to address the limitations of travel time tomography, the power of joint geophysical inversions, and the increased resolution when you use seismic waveforms. And so this image on the right shows a seismic source as the yellow star and seismic receivers on the surface across a volcano, and this orange square is the magma body. And this is a synthetic waveform study where in green it shows the shear waves, which I'm not going to talk about right now, but in pink it shows the P waves. And you can see that as the P waves pass through the low velocity of the magma body, they're quite severely indented and delayed. But because this magma body is relatively small compared to the seismic wavelength, there's wavefront healing. And so as this wave propagates beyond and up to the surface, that indentation more or less goes away on this seismic wavefront. So using first arrival travel times is difficult because these wavefronts bend around and heal after they've gone through a magma body. What we also see in this waveform simulation is that seismic energy that travels through the magma body is slowed down and then bent up to the surface at a different angle than the first arriving energy, and is quite diagnostic of the magma body. And so waveforms are quite powerful additional information. So that was a simulation for this experiment at Newberry Volcano, where the seismic source is over here to the northeast. This is the line of seismometers that were spaced very densely, 300 meters apart across the volcano. And this is the seismic record section showing the dense data across the top of the caldera. In red, it marks the first arriving seismic energy, which is what's used in travel time tomography. And then because of this very densely spaced data, we can actually recognize a coherent waveform in pink, which is this phase that I showed you passing through the magmatic system. So in that study, on the left here is another rendition showing in terms of rays now how the wavefronts bend around a low velocity. So this is in the first iteration of a tomographic inversion. You take a simple background model and you propagate rays through it, and you can see these nice evenly spaced rays. As a low velocity anomaly is built within this model, or as it slowly builds up in order to explain the travel time delays, you can see the energy propagating around the low velocity and also on the front and back sides here. And so once this energy wraps around the low velocity volume, you really have very little resolution of the structure within the low velocity volume. And so as soon as there's enough velocity drop to wrap energy around, then you can't really account for any further velocity drop. This synthetic model on the left shows that. So at the bottom is the synthetic that we generated. The top panel is a map view of a circular anomaly beneath the caldera. The caldera rim is in red here. And then there's a cross-section, again, the caldera in red, and now we look at the side of this cylindrical anomaly, and here you can see the high velocities that surround this low velocity anomaly at Newbury. If you trace seismic rays through this structure and you invert, you obtain this panel over here, the leftmost on the right, where we are only able to recover a minimal velocity drop, even for this large velocity anomaly that corresponded to a purely molten magma chamber. And this is a comparison between that synthetic recovery and on the rightmost, the observed. And so really this means that from travel time tomography, any model between a minimum velocity drop as is shown from the observed tomography and a fully molten magma chamber is actually allowed. So one way to start improving on that is to do a seismic inversion where you incorporate more than one kind of seismic data. This is an example from Ben Heath's work using seismic data with complementary coverage. And so the previous data is shown in red here, and then teleseismic phases are added. One example is shown as these blue rays to illustrate that now the energy is nicely crossing, and this gives us some better resolution. The lowest panel on the left shows the teleseismic seismic waveforms, and I could talk in more detail about that if you would like later. The result from this joint inversion, let's look at panel B here, here are the perturbations from the joint inversion. We now have a velocity drop anomaly of over 10% in this area, where previously in the model we had only recovered about a 5% velocity anomaly. We also have better depth coverage because we've added these teleseismic phases. And this is the additional velocity drop we've now recovered is a 5% difference. So that is one step forward. And of course, you can also include seismic data that is sensitive to sharp boundaries, and you can go further in the teleseismic study by using different frequency contents. In Beachley's work leveraged the waveforms. This was a forward modeling exercise where this coherent waveform that we recognized as a secondary waveform. This is a zoom of the previous record section I showed. And this was the tomographic result in that case. If you propagate seismic waves through that basic tomographic model, you reproduce the first arriving travel time, but that's it. You don't reproduce any of the loss of energy here, and you definitely don't produce a secondary arrival. And so by forward modeling a couple of geologically reasonable models, we found a couple of members of these families of models that fit the data, included a graded mush model where there's more crystals settling at the bottom, a model where there's crystals more or less evenly distributed within a magma body, and a purely molten sill. And these three models explain this data more or less equally well. These are the waveforms for the mush model. And they produce a secondary arrival and some loss of amplitude in the first arrivals. And so now we're starting to narrow down from some minimal model to a maximum of purely molten to a more narrow range with a higher melt fraction than the minimal model, but not all the way to a purely molten model. The next step in using waveforms is to do full waveform inversion. And I'm going to show you an example from the Santorini data set where we had dense 3D coverage. And this is using the portion of the data over this large and very active seamount, seismically, magmatically active seamount to the northeast of Santorini. And in order to do full waveform inversion, you need very dense coverage of the seismic waveform in order to be able to reconstruct its propagation. And you also need a very good starting velocity model so that your waveforms are being modeled within the right portion of the data. This is an example at the bottom of some data here where the way it's shown is panels of synthetic data through the tomographic model and then observed data. And then after full waveform inversion, there's less difference from portion of data to portion of data. This is 1 second of data was modeled with increasing frequency content. So I'm going to show you only how the full waveform builds up anomalies relative to the background tomographic model. And after 20 iterations and the incorporation of sort of low frequency data, you already start getting a pronounced low velocity anomaly right beneath the seamount at 2.7 kilometers depth. And then as you go through more iterations, the velocity anomaly builds up to about a 30% reduction in velocity. The width of this anomaly is about 3 kilometers and it's about 1 kilometer thick. So it's definitely something that's hard to resolve with travel time tomography because of the wavefront healing. And so it's the secondary arrivals that are interacting with this body that are very important. And I sketched in a cartoon object that was about at the right depth and width and height on top of our image from the tomographic results to give you an idea of how that looks. And so the point I really want to make here is that seismic imaging provides a family of possible velocity models and that there are various approaches to narrow down what that allowable range of models is. And of course, the ideal is to start bringing in other data beyond just seismic data. Okay, so then what are the actual melt fractions that are represented by a particular low velocity anomaly? And so I'm going to talk a little bit about possible advantages in rock physics that could help with this problem, then talk a little bit more about how other geophysical observations can be brought in. So P and S waves are very sensitive to melt geometry. And so typically this sensitivity is analyzed using semi-analytic methods that include simple oblate ellipsoid melt inclusions. And these methods include differential effective medium methods and self-consistent methods. This figure on the right shows different aspect ratios. So that's the ratio of the long against the short axis of these ellipsoids. And their impact on the P wave velocity up here and the S wave velocity down here. And so you can see that for a P wave velocity of about 4.7 kilometers per second, if the melt is distributed as thin films with an aspect ratio of 0.01, we would infer a melt fraction of 9%. But if they're distributed along in tubes or at the grain corners only, then you would infer a higher melt fraction of 23%. So that's a big range for one particular velocity. And if the melt is organized in tubules, you would get 32% melt fraction. So this unknown of what the melt geometry is leads to a large amount of uncertainty. If we include shear waves, we can make some progress. For this same P wave velocity, we get a shear wave velocity of about 2.2 kilometers per second for both melt that is in with an aspect ratio of 10 or 1 or 0.1. But if the aspect ratio is 0.01, we would expect a very different shear wave velocity for that same P wave velocity. So for small aspect ratios, this VPVS ratio, or the relative drop in these two amounts, can start to be very informative. Digital rock physics is one way to improve on these semi-analytic methods. And the real idea here is to also leverage, can we actually use geologic microstructures to give us a better idea of how melt is really distributed in a mush? And so in this idea, this concept is to find geologic mush fragment samples, to make X-ray scans of them, to reconstruct the sample porosity and permeability from these 3D X-ray scans, then to build a virtual rock sample with finite elements, and then to use numerical homogenization methods to model the elastic response of that geologic sample. And so these homogenization methods include dynamic or static methods. Polato et al. Have worked on this. They've done an example for one rock, a gabbro-cumulate from St. Kitts, KS21 is the name of the sample. The sample has a melt fraction of 14%. It's actually relatively anisotropic for P and S waves. And when you compare the mean velocity that's obtained for P and S waves here against these semi-analytic methods, in this case curves from the differential effective medium method, you get a effective aspect ratio of about 0.1. So now we could go back to our seismic observations and have more confidence in the kind of aspect ratio that we should choose to make interpretations of the seismic data. Of course, more than one sample is needed to actually map out what the appropriate curves here are. And then seismic waves are sampling at a longer wavelength than just the microscale. And so we also need to include geologic information on the mid-scale melt distribution, for example, veins and dikes and sills. I talked about the importance of shear wave velocities. I'm going to come back to Mount St. Helens a little bit later, but VPVS tomography at Mount St. Helens has found a high VPVS body, so a body with relatively low shear waves compared to P waves. Directly beneath Mount St. Helens, that's this body F1, between 4 and 13 kilometers. There's a similar body under the Indian Heaven volcanic area to the southeast of Mount St. Helens. In the lower crust under Mount St. Helens, there's a high velocity anomaly directly beneath the volcano with the relatively low VP offset to the southeast. And the deep, long period events that are found at Santorini that are thought to be reflective of magmatic fluids are on the boundary between these bodies. And I'll get back to that more. But certainly these high VPVS regions are inferred to correspond to the presence of fluid, and they correspond to this column of earthquakes as well. Of course, electrical conductivity is very sensitive to melt distribution, and in particular to permeability of melt. And so I just wanted to show you this resistivity image from Weishan Volcano in northeast China by Gao et al. And they used 99 magnetotelluric instruments at 1 kilometer spacing across this volcano. And have recovered a resistivity image that extends through the upper 15 kilometers of the crust with an upper crustal magma system and a mid-crustal magma system, and what appears to be a relatively narrow connection between them. They use a combination of the shear wave velocity in that area and the conductivity to get at melt fraction. And so first they use the shear wave velocity in the area to infer what the melt fraction is. And this is using one of these very simple relationships between shear wave velocity and melt fraction. And then given the melt fraction, they can infer the water content as well, because conductivity of a silicic melt depends both on the melt content and the water content and is quite sensitive to both. So you need more than just conductivity to help narrow this problem down. Another example of a joint inversion of complementary data is this resistivity inversion that is constrained. In this case, the inversion is constrained by the geometry of the slab that's seismically imaged, and it allows a resistivity image to be recovered that shows the source of melts for these crustal magma storage regions. And so it's important for us, especially within the subduction zone collaboratory, to think about connections and magma inputs from the subduction zone. Oops. I'd also like to address what is the structure of the mid and lower crustal magma storage systems. We'd like to know the nature and composition of mush, the depth and connectivity of different reservoirs, how intrusives act in this, what is the thermal structure, and what observables are sensitive to these structures. So this is the image from Mount St. Helens. There have been, one question is, what are these high velocity regions? What magma transport paths do these models favor? And what is the thermal structure and the rheology of the lower crust? What's the background state? So there have been interpretations that suggest that this low velocity anomaly is the lower crustal magma storage region that's offset, and that magmatic fluids are moving to the northwest to Mount St. Helens in the lower crust. But more recent suggestions are that melts are actually moving up through these lower crustal intrusives, which are the high velocities, in a more direct manner. And that's consistent with what Tom Sisson was suggesting in his talk in January in this session. And so it's interesting, what kind of magma transport paths are actually favored with models that include the physics and chemistry. And I think for time's sake, I'm going to skip this. Okay, so a summary of what we do not understand. We can improve resolution of the structure of magmatic systems by really keeping in mind that travel time tomography allows you to look at a family of possible models, and that we can obtain increased resolution if we include waveforms and complementary kinds of seismic data, that we could make advances in rock physics to predict seismic properties using real geologic micro and mid-scale structures, that other data is also sensitive to the geometric distribution of melt, and that there's real power in joint geophysical inversions. And then a series of questions about intrusives and magma transport and the thermal structure and rheology of the lower crustal magma storage area. Now I'd like to quickly conclude by talking about a couple of models, and talk about forward modeling, which allows you to explore sensitivity of data sets and to test hypotheses by informing the design for data collection to specifically address hypotheses, and then different avenues for joint inversions of data and models, where data can be used as constraints, or models can guide the exploration of data space. So this is an example from Yellowstone, from Ruber et al., where they did a geodynamic inverse problem. So they use a viscoelastoplastic rheology. They constrain the geometry of the magmatic system from the mantle plume in the asthenosphere up through the lithosphere, lower crust, upper crust, and with the goal of fitting the gravity and the geodesy, and the tomography is really just used to constrain the geometries. So the parameters that they're exploring are the rheological behavior of the crust and the mantle, and the density contrasts between these different regions. They found that 3D effects are important, and as this figure shows with the different sized circles, the sensitivity of the surface observations to different parameters can be explored. They studied the connectivity between different reservoirs and found that the observations require connected reservoirs. They explored the rheology of the crust in the lithosphere and found plasticity near reservoirs and weakening of the lower crust. Similar models can be used to look at, to forward model geophysical and geochemical signals. And so this is an example from Joe Dufik's group showing a magma dynamics model that's coupled with phase equilibria from rhyolite melts. And then the outputs are converted into parameters that can be then forward modeled to compare with other geophysical observations. It's important, the background state with which you start these kind of models matter. What's the crustal structure, composition of the crust? What's the thermal structure? And then these models take aliquots of melt from the mantle, and their spacing and volumes matter. So this is an example, 2D slice through 3D model showing the evolution of the temperature field, the coupled calculation of melt fraction, and the major element chemistry of the melts there. And if you focus on the shallow magmatic system and you track particles within this system, you can look at the crystal scale zircon evolution. So this is going to show zircon crystals at these locations 1, 2, 3, and 4. And you can see them grow and shrink and add zones with different uranium content as they evolve within this magmatic system. So this becomes interesting for comparing with populations of crystals and what they tell you about the dynamics of the magmatic system. To forward model geophysical data, you need to then map from in the top the temperature and melt fraction to in the bottom the S-wave velocity and the electrical resistivity. And so as I've talked about earlier, those are also, we need more information on correctly making those mappings. And then we can take those subsurface distributions and then have to make a computation to actually compare them to observations at the surface and the sensitivity to different internal structures. Lastly, I just wanted to point out that there's also the question that'll be addressed in the March series of eruption and diking from magma chambers. In the upper diagram, rheology is taken from a seismic tomography model, then a finite element model for deformation is built. It includes a shallow weak layer within the caldera, which leads to lateral dike propagation and extrusion near the caldera rim. And this is similar to cases of unloading a caldera, as shown in the lower figure. So again, the tomography results can set a background for understanding deformation, but there's several steps to go through here. So in conclusion, to leverage geophysical observations and modeling of magmatic systems, you really need to look at multiple length and time scales. In forward modeling, we're seeking to replicate aspects of the physics and chemistry, and we need to know mapping relationships well. Forward modeling allows us to test hypotheses so we can inform the design of field data collection to look at specific end member models. And we can study the sensitivity of surface observables to subsurface features. In inverse modeling, we can find best families of model that reproduce certain inputs and bring in different data to narrow down possible families. We can do joint models with data that have complementary sensitivity to structures to get higher resolution results. And we can do joint models that don't just fit observations, but also include the actual physics and chemistry of the processes, so that we have an entirely consistent physical system. Thank you.
Thanks, Emilie, for the great talk. And we will move on to the Q&A session now. So the first question to the attendees, please use the Q&A feature to ask your questions. The first question to Emilie is from Paul Siegel, and the question is, recent imaging studies are interpreted as revealing stacks of seals, as for example, axial, but also at Mount St. Helens. How robust are these interpretations, and how should we interpret the impedance contrasts required by the data?
I think that there definitely are stacked sills, and there's certainly observations at a number of volcanoes that suggest this is the case. I think it would be really interesting to and informative to do waveform propagation through some of these models to really be able to look at what the implication is for a range of seismic observables, and also look at other data sets that would help to constrain those kind of observations.
Yeah, thank you. I mean, it would be really helpful to have some idea of what kinds of constraints on the physical properties would be in order to reproduce these reflected phases. And, you know, are we talking about large contrasts and things like, say, melt content, or could they be more modest? I mean, in some places, I mean, I found it rather surprising to get that result at St. Helens, for example. I don't know if others share that, but it wasn't the conceptual model I had in mind. And certainly the tomography tends to show these more blobby features. So it would be really helpful to get some hard constraints on that.
I'm not super familiar with that paper, but I think that you can do modeling to look at the amplitudes that are observed, the thickness and of layers and their internal properties and what ranges are allowed. And then you could turn around and see if that's consistent with other observations.
Yeah, thank you.
Okay, it looks like there is no additional question at this time, so I suggest that we move on, given time constraints. Please, if you have questions for Emilie and you didn't get a chance to ask it, feel free to type it into the Q&A form. We will capture it, and Emilie will have the opportunity to get back to you via email. So thank you once again. And again, for those of you, the next talk, Chris's talk, if you have questions, use that Q&A feature.
All right, so our next speaker this afternoon is Chris Huber. Chris earned his PhD in Earth and Planetary Sciences from Berkeley for work on the importance of small-scale dynamics on large-scale magmatic processes. Chris was a postdoc and later associate professor at Georgia Tech before moving on to Brown University in 2016. He studies geodynamical problems on Earth and other bodies of the solar system, and more specific to the MCS, he develops theoretical and numerical models to understand the evolution of magmatic systems over a range of different scales. His interests include melt production and transport, bubble dynamics, porous media flow, and diffusion timescales in crystals. Chris's talk today is titled Modeling Magmatic Processes. Which model is appropriate for what? Chris?
Just to mute myself. Yeah, thank you very much, Kyle. Before starting, I would like to really thank Helge and Kyle for the organization of all these events. I think we all benefit from it. So this is more like a perspective talk discussing about models and what we've learned so far. And as you do those kind of talks, it's very common to forget some very important piece of work. So I'd like to apologize before I start for the people that have contributed some very important piece of work that I may have forgotten here in the interest of time. So as we're working towards those kind of collaborative measures, both the MCS, but also SZ4D, I start to ask myself a few questions, and I think it might be useful to frame this talk along those lines. For instance, if I was to collect a rock and analyze its rock composition, and if I have geothermometers and geobarometers to constrain temperature and pressure, for say, and the question that I would like to answer is to understand the state of the magma under those conditions, then I think for most of us here on this call, we would think of a thermodynamic model to address this problem, such as, for example, melts or any of the other ones that Mark mentioned 2 days ago. And I think it's quite special that we have now adopted into both our educational framework, but also research framework, a fairly common approach to these problems. As Mark mentioned, there's still some caveats to melts and any other models like this. But as a community, I think there's a clear endorsement for those types of models. Now, if you repeat the same question, but frame it in terms of the dynamical evolution of a magmatic storage system, for example, and you can think of thermal evolution, of the rate of fractionation between melts and crystals or bubbles, and you ask yourself, what kind of tools should you use actually in those conditions? I tend to not be sure exactly what to do there. And as a modeler, potentially what I might end up doing is develop a model on my own. And that begs two questions, which are basically at the center of this presentation. The first one is, there's a fair amount of models that do exist in terms of dynamics. They have very different strategies and scopes. Among all those models, as a user, which one should you go for and why? And I'll try to talk a little bit about that going through different types of models in the next slides. The other that is related to MCS is to ask ourselves why. Is there a lack of centralization of the modeling efforts in terms of dynamics? And perhaps part of it is a lack of coordination or effort of the community in that direction. And I think that's partially true. But I think there's something also that is quite different when you move from thermodynamics to dynamics, which is the problem of scales, both temporal and length scales. And I'll talk about that a little bit. But the main essence here is that as you study different dynamical processes, you may have to use very different tools to do so. All right, so I'll start with conclusions, which is quite unusual, but this is not the typical kind of talk. There won't be much research discussion here, but the first take-home message I'd like to do, and then you can probably doze off if you want to do something else, is that by construction, physical models, and by physical models, I mean both physical and numerical models, they're not meant to provide an accurate depiction of what really happens in magmatic systems. And I think there's multiple types of reasons behind that, some of which are deliberate, some are not. The non-deliberate one, I put this first, like the gap of knowledge here, and it could be two types of gap of knowledge, one of which is directly related to what Emilie was just talking about. It could be the lack of understanding or the poor constraints we have on initial and boundary condition on the systems to run dynamical models. They're hard to get, they're not really accurate. We don't have very clear ways to get at them. And the second type of gap of knowledge relates a little bit more to what George was talking about a month ago. There are fundamental gaps in our understanding of how dynamical processes work. And that's where the work that, for example, E and his group and other groups have been doing on granular mechanics could be fairly important to address those gaps. So the second one, basically something that models themselves could address to some extent. Now, there are some other reasons why physical models are not meant to provide this accurate depiction, and they're deliberate. So one interpretation is that we have a tendency to try to go for simple models to explain things. You know, that's the Occam's razor principles that we're all fairly familiar with. There are some drawbacks to that, and I don't think sometimes in science it's appropriate to think this way. Many times it's not. It's not because it's simple that it is correct. I think a better framework to think about that is this principle of falsifiability that is very important and inherent to our research. Basically what it means is that we want to build hypotheses that can be testable, and that the model should be able to tell us whether we need to validate or can validate this hypothesis, or we need to find another one. So I'll come back to that a little bit later during the talk. The second take-home message that I would like to put forward is, for me, and that's my perspective, models are really designed to address causality. That's what models are really good at. Say, for example, you're interested to look at the growth of a magma storage region because of recharges of magma into it. A model could potentially tell you, if I increase the recharge rate by a certain factor, this is what happens. So they provide you with links between cause and effects. And that is great in some ways, but is also potentially a challenge. Why? Because it means that the model, or the design of the model that you want to use, is not independent of the question or the causal link that you want to study. And in a field like ours, where there are people coming from very different perspectives on problems, it means that there's a zoology of model that do exist here. And that's one of the issues that I've been talking about in the previous slides. There's pros and cons about having a large number of models like this. Pros is that you can have models that try to look at the same thing slightly differently, and we can learn more about it. They could validate or invalidate each other, which is basically leading to progress. There's also cons. And one of the big cons is for the community, the fact that it's very hard to identify what is the right tool for the right job. And another conclusion, which I will come back at the end, and it relates to some aspects that Mark basically mentioned 2 days ago, I think very eloquently. We need to be thinking, and I think that's something MCS should be able, should be a good vector actually for doing this. We need to be thinking about adopting better practices in terms of how we approach modeling. This is the most dreaded word in modeling. Benchmarking is horrendous to do. There's very little excitement to go through those exercises, but they're very valuable. We don't do much of it. Even validations are far in between and sparse in our field, and sometimes really validating models against conditions that are very far away from their applications. The other thing that we're not really good at, I think, is being transparent with regards to the assumptions that the models are basically built upon, but also their limitations. Mark alluded to the problem of access to models and codes. I'll come back to that in a second. One thing that I don't think we have discussed much at this stage, which I would like really to put forward to the community, is training. I think MCS should do something about that. I'll come back to that later. And not only in terms of coding, but in terms of the math and the physics behind the physical models that we want to use. And the idea is the following. If I was to step into a clean lab tomorrow to try to do some analysis, the person should be really careful and worried about this, right? I don't have a training to do it. I'll probably do a very dangerous job or a very poor job at it. So I will have to basically undergo some kind of training before I can even step into that space. In terms of modeling, our codes are basically our labs. And destroying a code is not too much of a problem. We can fix it. But for you to be able to use a code in its basically intended way requires a little bit of physics and math expertise. And I think there's a lot of opportunities here to basically build those training opportunities. All right, so now what I decided to do is for the next 10 minutes or so, we'll go and visit some of that zoology of models that I talked about before. And we'll look into very different strategies of models. And I mentioned that models are usually designed to address a question. And they're not necessarily meant to address questions that we're not designed for. And that's kind of the idea behind what I will be talking about. And we'll talk about what we learned about these different types of models along the way. All right, so the first type of models, to go back to what Tom Sisson was saying in January, he talked about the long-lived systems that we find now, the evidences for magmatic systems that can be active for hundreds of thousands of years to millions of years in certain cases. And the fact and the recognition that those systems grow incrementally has led to a lot of interest in terms of understanding the thermal evolution, the longevity of those systems, try to model them. What does that imply in terms of magma flux through the crust, which is something that is very hard to constrain otherwise. And so there's been a fair amount of models actually looking into those problems from different standpoints, looking at zircon crystallization spectra here, for example, on the right, all the way to the accumulation and formation of melt pools that could be later remobilized for eruptions. And we learned a lot from those models. They brought a lot of very key and important conclusions to our field. I think one of the main ones is that to maintain an active storage region that is capable of sustaining volcanism requires a very high mass flux to the shallow intermediate crust. And the second is that latent heat can play a fairly large effect, especially for silicic mushes as they cool closer and closer to their solidus. And that thermal maturation is key. And that's something that Emilie just mentioned in a previous presentation. Matt Jackson also talked about thermal maturation and its importance in developing those large and extensive magmatic systems. Now, those models, they also open the door to new questions, right? If you have a large flux of mass in the shallowest parts of the crust, then there's a mechanical cost that is incurred to do that. And those models were not geared to study this. So we need to look into that, and that's where we're going for the next slides. The other aspect of those models that I just presented did not account for mass transfer or mass movement outside of the emplacement of those sills over time. So therefore, one could ask, what is the effect of phase separation on the longevity and the cooling rate of the mobile part of these systems? And another question here is there any role, especially if you consider the shallow crust, of an exovolatile phase on longevity and the evolution of those systems, both thermally and mechanically? So we'll try to explore some of that by looking at different kind of strategies of modeling. And for instance, mechanical models, which have been developed independently from the problem of thermal modeling, but given these high fluxes have become very important. And this is the seminal work of Mark and Don actually in 2003, an open system with magma recharge and the evolution in terms of pressure, but also a simple coupling, viscoelastic coupling with the host crust, and try to understand how you form large magmatic systems at relatively shallow depth. And one of the key things that they found is this positive feedback between large magma chambers being able to grow more without erupting, because it's more difficult to basically build up pressure in them, among many other things. And people have worked more on those problems. I've been part of that with Wim de Gruyter, looking at slightly different aspect, but still motivated by the seminal studies in 2003, looking at different trigger mechanisms and having a slightly different kind of coupling, especially looking into phase change in crystallization within magma chambers and their effect on the dynamics. And, you know, since then there's more work and more development of really cool ideas, like the ideas of mass exchange between a mush and a crystal-rich region, crystal pore region upon recharge, and how it basically both affects the magnitude, but the timing of the peak pressures and potentially therefore of eruptions. And even more recently, work looking into more complex coupling between the crust and the magma reservoir in terms of outgassing and opening dynamic permeability pathways for gases. So we learned a fair amount, I think, from these models. They're quite simple, so we can run a lot of those. There are lots of different pressure dissipation mechanisms that we can think of, not only including the rheology of the crust. They can mitigate the buildup of overpressure, therefore the response of magmas to recharge, and therefore their growth rate as well. That being said, though, the large magma recharge rates that we see and the fact that we are all interested about volcanology here means that we have a fair amount of events that leads to fracturation of the host and the formation of dikes that sometimes can intersect the surface. And those models are not really well developed to study this, right? The coupling in terms of rheology between the crust and the magma reservoir is fairly simple. All right, so we can move forward with that. If you're interested to understand what happens as the crust is basically being pushed around by the storage region, there's a slew of models that do that extremely well. So on the left, this is part of the work that Trish Gregg has been doing for the last 10 years, in this case with Shanda Silva, and looking at different rheologies of the crust in response to a pressurization of an oblate cavity, the magma chamber in this particular case, and the development of heterogeneous distribution of stresses around the magma chamber. Gerbeau on the right actually does that in 3D, similar kind of calculation, but different kind of crust rheology. And those models, again, they offer a lot. They, first of all, show us how heterogeneous the stress distribution around the crust is, which is not captured by the previous models. They can test different types of rheology of the crust and see what controls it exerts both on stress concentration, but on the formation of different types of faults around the system that could lead to the eruption. And for example, one of the things that Trish Gregg has been showing actually is the different types of triggering mechanisms that you can have under different circumstances in the systems. So they're really the best models to look at the crustal response around the magma storage region to, for example, an event of recharge. However, like all models, they have their own caveats. For instance, that the stress is prescribed or the strain rate is prescribed, and therefore not really coupled to the internal dynamics of the magma body. And so if you want to understand the internal dynamics, then even in a further or deeper actually level than what was shown in the previous model, that's where you need to look into what happens in a magma reservoir, right? So there's been a lot of work done on the fluid mechanics aspect of magma chamber dynamics or storage regions. I'm jumping here ahead to models that really consider multi-phased processes, and in this case, on this slide, continuum approach, meaning that both the dispersed phase here, crystals on this first diagram from George about 20 years ago, the dispersed phase is approached as a continuum, and so is obviously the melt. And there's a variety of models that have been done looking at the effect of the difference in densities between the dispersed phase and the host phase in driving basically convective motions. Even more recently, there's been work trying to look more at this melt crystal separation within this framework, and that isolated those two regimes of melt separation, some at low crystal content by the sinking and the separation of crystals from the melt by crystal settling, for example, and some later stage and fairly efficient processes such as compaction to expulse the melt from a cumulate region. And there's more work that has been done. This is a relatively recent paper looking at the effect of buoyancy as you inject the magma from deeper with a slightly different composition and different volatile content. So the effect of buoyancy in building up a very interesting kind of patterns of pressure distribution in the shallow storage region. So we learned a lot from those models. Obviously, there's still much more to learn from them. One key lesson, I think, that I want to emphasize once more is that although in some textbooks or some conceptual ideas, very often thermal convection and movement into crystal pore magma chambers is often viewed in light of the Rayleigh-Bénard kind of thermal convection analog. I think it's a very poor analog. Motions in magma chambers are driven by density, sure, but not really by thermal expansion problems like it is in Rayleigh-Bénard. So the contrast in density between the different phases in magma chamber is quite important. Their motion is quite chaotic and complex, which is important when you interrogate the crystal record like Philip was talking about. You can have very different responses. I'll come to that in a second. And there are different modes of phase separation in the systems. So those models, they continue to prove their value. There's much more that they can offer, I think, but they have their own limitations, right? For the most part, those models are closed systems. So by that, what I mean is actually the overall mass in the total system, even if there's more than one reservoir, is fixed. And the coupling with the surrounding crust is relatively simple, right? It's mostly boundary conditions, sometimes a little bit more sophisticated. The other thing that they offer, which we talked quite a bit about a month ago between the talks of George and Matt, is the role of the dispersed phase and how a continuum approach could be sometimes limiting in terms of understanding the dynamics and the mechanical feedbacks between melt and crystals, for example, as it is parameterized in those models. So Over the last decade or so, there's been a lot of effort going in that directions of granular mechanics. And there's several groups actually that work on those. I'm sorry if I forgot some of the different studies, but it's quite an active system now. On the left, here in the context of looking at the evolution of crystal populations, you have the work of Gillian Schleicher and George Bergantz a few years back, looking at the mixing bowl. And at the bottom, actually, the left part, you see the different, basically, trajectories of crystals that were relatively nearby each other at some points, and how the difference in trajectory caused by the same event could record different information, which is consistent, slightly different kind of setup, though, with what I'm showing here in this GRL paper in 2019 by Kula et al., looking at the formation of zonation in plagioclase in crystals that basically share the same kind of evolution in the plumes sinking from the top of the reservoir, for example. Those granular mechanics approach offer, therefore, like a lot of interesting alleys for petrologists, but also for people more interested about the mechanics of those systems. So these are still those kind of granular approaches. On the left, this is a very recent paper from Alex Carrara, working with Alain and George on these problems of mush dynamics. And it's a really neat study, if you haven't looked at it, looking into the injection of, in this case, I just took one of the movies. It's dense melt injected at the base of a mush and the rheological response of the mush to it. This is a partially resolved model in terms of the fact that the crystals are all resolved separately. However, the coupling with the melt is at the scale that is greater than the scale of a crystal. And that is great because it allows you to look at much bigger length scales. If you want to go to fully resolved, meaning that you really resolve boundary layers around each crystals in terms of fluid dynamics, this is an example of a really neat paper that just came out about a year ago in the Journal of Computational Physics, looking at the shearing of suspensions, and actually quite an achievement, looking at suspensions not only of monodispersed disks, but also squares, as you can see at the bottom. And from those calculations, again, George talked about the importance of force change. You can see them in the second panel from the top. The important part here is that there's a slew of very complex nonlinear dynamics that you can start to look at. And that leads to highly nonlinear rheologies of those suspensions. So that opens the door to a new understanding that will become really critical. You can go a little bit further. This is basically some work partially published, I guess, that we're doing with lattice-Boltzmann methods. On the left, looking at polydispersed suspension in 3D. Those are fully resolved. And on the right, looking at suspension with 3 phases. They're tricky, and there's still a lot of work to be done, but you can go that way too and learn a little bit more about those processes. So the frontier is really to look into crystals of different morphology, different sizes, and also start to put deformable bubbles into the mix. There's lots of work to be done. So what can I learn from those granular mechanics models? I think it's obvious, and over the last 5 to 7 years, we learned a lot from them. And this is a goldmine for us to keep working on them. They're fundamental. As we strive to understand how mush basically evolves in those storage regions, we need to basically build this understanding. Now, we don't have only numerical models to rely on. I think we also can really bank on experiments. I'll come back to that in a second. I think there's a difference between steady state experiments and also transient experiments that is important to explore. Now, there's some caveats to these models. And Mark made a very good point on Tuesday, talking about the fact that models are even more powerful when they're accessible to everyone. Those models are not. They're really complicated to use, but more than that, actually, they require large computing resources. So it's not really likely that everyone can basically play and modify things to address new questions with them. It requires an expertise and structure around you to be doing so. On a more fundamental level, the more complex the simulations become, for example, in those granular medium, the more factors they depend on in terms of outcome. For instance, when I did this calculations, or people do this calculation of shearing a suspension, the disposition of those crystals inside your domain, their position, their orientation if they're not spherical, the position of bubbles if you have a third phase with respect to crystals and melt, all become fairly important and will have an influence, sometimes quite significant, actually, on the outcome of the model. So that's okay, but there's two problems with that. The first one is, in the real world, when we try to look into what could have happened in a magma reservoir, let's say prior to an eruption, you don't have access to this information, right? And that means that the real approach here is to explore parameter space. But with the complexity and computational cost of those models, this is not something easy to do. You have a parameter space that is growing with complexity, but with complexity is also growing the computational time. The other thing that is quite difficult here, and I'll come back to that in a second as well, is understanding really the outputs. You start to have so many dynamical feedback here that sometimes it's not an easy job to basically really come to a simple conclusion. And to me, that brings up a question, or actually not really a question, but a statement. The more complex a model becomes, I think the more it is geared towards addressing some fairly simple question, because it becomes very difficult to have a tractable problem sometimes. All right, so I would like to now use that to try to think about the questions I framed at the beginning. We talked about the fact that MELT is one of our go-to models to look into thermodynamics, into magmatic problems. And I think that's a huge plus for the community, because there's knowledge, there's basically some confidence using it. Is it reasonable for us to strive doing something similar in terms of dynamics? I think it is to some extent, but it might be very difficult. And I think the problem is here, not only the effort, but the problem of scales. I mentioned that before. Dynamical processes span a very wide range of length and time scales, at least the ones that we're interested in. And because of that, it requires slightly different tools sometimes. And I think that will be something that we'll have to figure out. And I'll be interested by any comments you may have in this. The second question or comment here is it reasonable to strive for a fully resolved model of magmatic processes, a granular scale model that will allow us to basically span, for, let's say, for example, the transcrustal column? I think we're pretty far away from it, both in terms of technological advances, but also in terms of our understanding of the physics. Is it something that we should go to? I think it's appealing, but I'm not sure it will be the solution to all our problems. So some of you may know the book, The Hitchhiker's Guide to the Galaxy from Douglas Adams. I'm not a big fan of sci-fi, but this is a fun book to read anyways. And one of the point in the book is that there's this advanced civilization that builds this computer deep thought to answer the biggest question of all, the meaning of life and everything, right? And the computer takes about 4.5 billion years to find an answer, which basically is here, 42. Nobody can understand the answer, so they have to build a second computer, equally complex, and run it for an equal amount of time to basically even understand the outcome of the first calculation. And I think that's a little bit what I fear with those very complicated models. At some point, really extracting useful and applicable information out of them might become very difficult, but we should still probably strive to do it. The second thing here is, again, going back to this principle of falsifiability. When you have a model that is relatively straightforward, it's easy to invalidate or validate an hypothesis. And I think with models becoming more and more complex, we need to find ways to do that efficiently as well. So if we cannot go to the fully resolved models, at some point we'll have to consider upscaling. For those of you who haven't looked at this paper from Tobias and Jenny, actually 2 years back, this is a really neat model. And I stole this figure from the beginning of their paper, where they look at different scales. You have the local scale, which for us is a granular scale, and the system scale, which will be potentially your crust, if you think of it. Upscaling is awful. I've been banging my head against the wall with upscaling for more than a decade now. The idea of upscaling is to simplify things, right? And I think upscaling requires a very deep understanding and knowledge of granular scale dynamics. I totally agree with George. Just to understand the costs and limitations and make informed decisions as to what information we're okay to basically remove or neglect from our models. I don't think simple homogenization method will likely do any good to us. The problem is here at the granular scale, as you expand, we know that the number of descriptors that describe the topology and the evolution of the topology of these multi-phase systems go well beyond crystallinity. We need to understand the fabric tensor. We need to understand a lot of different things, connectivities. And that means that we need evolution equation for each of those kind of factors. And that will take a lot of effort. Moreover, I do believe that those are a temporal memory to them. And so that means that all our scaling laws and upscaling laws should have basically memories into them. I will skip the second point about fractional law. We can talk more about it at some point. But I'd like to make a comment. I talked a lot about rheology because it's a very important problem and frontier problem in terms of understanding how much behave dynamically. A lot of rheology experiments really toss out the transient evolution of a suspension to focus on the steady state to try to infer basically, okay, for this kind of stress conditions, this is the amount of shear rate you should expect, right? I think we need to really look into transients in those systems because there's lots in terms of granular mechanics to be learned from those. It's a little bit like kinetics has been for geochemists moving beyond thermodynamics in some ways. All right, so what do we want from MCS? I don't know. These are thoughts and will be good to discuss them. I think, and I agree totally with Mark, there's a need to define better practices. I really like the idea that Mark put forward in terms of Jupyter papers, which allows people not only to look at results, but reproduce results and potentially play with the models. I think MCS could help provide some funding or structure to migrate codes from softwares that are proprietary and just go to open and free softwares. That aligns pretty well with what Mark was talking about. Additionally, I think that MCS could advocate for incentives, both from funding agencies, but also from employers, right? I'm a tenure track, or I'm a tenured faculty now in the university. We have some credit for the service that we're doing. I think a huge service to the community would be to really spend time, make those codes free and available and easily accessible to everyone, and should be rewarded as such. The other thing MCS could do is that we're not the only one looking into granular mechanics. We're not the only one trying to code complicated problems or look at large data sets. It should be also a platform to collaborate with experts that have been thinking about the same problems or slightly different problems for as long, or if not, sometimes even longer than we have. All right, I'm done and happy to answer any questions.
Thanks so much for the great talk, Chris. Anyone that has any questions, please type them in the Q&A. I'll ask a quick question while we're waiting for some to come in. I'm wondering, at the moment, what do you think the biggest barrier is to that fully resolved crustal model? Is it the lack of understanding of the physics, or is it really the computational restrictions? Are we waiting for the next increase in computation power to come along?
It's a very good question, first of all. There's a little bit of both. There's something that George said that is entirely true. As you go to granular mechanics, the complexity of how you approach problems gets lower to some extent. You know, it becomes Newton's law, and that's as simple as that. But the amount of variables that you have to deal with, size, shape of crystals, everything else, and the numerical cost associated with it becomes tremendously large. So I think there's a technical aspect, but there's also, how would you validate those kind of problems? We need to do a lot of experiments, find basically benchmarking. And as the systems get more and more complex, this becomes also a more difficult issue.
Great, thanks.
So we have the second question for Chris from Einat. Excellent talk. You mentioned a need for experiments to test models. Can you elaborate on some experiments that you would like to see done?
So I mentioned that experiment looking at transient when looking at granular mechanics would be really interesting, even in terms of rheology. There's this really cool paper. I'll give you an example. I showed you this lattice-Boltzmann calculation where we're trying to shear some suspensions. And one of the things I was really interested is to look, if you have a porous plate on the top, as you shear suspension, there's dilation, so some of the melt actually comes out. And I was trying to look at the dynamic evolution of that. And there's a big, very beautiful paper in PRL in 2011 from Boyer et al., working in the group of Elisabeth Gazelli in France. And what they were doing is doing that experiment perfectly, actually. And they had those transient curves at the evolution of the volume fraction of particles, which tells you about the repacking of the mixture as it's sheared. And they tossed that over. I asked them to get the data. I said, well, we don't rely too much on this data. We're not sure exactly what to do with it. So now we have the steady states. And to me, steady state is really cool, and we can get something out of it. All the transient actually here is missing. So that's one example. I think there are lots of things in terms of granular experiments that could be done that will help models being validated. Did I answer your question, Anna? Okay.
Why don't we, there is a question from Joanne Stark, maybe to Emilie Hooft, so maybe we can address that question.
Yeah, so the question was, if we have a solid rock sample, a sill that has a variety of crystal sizes and matrix, multiple injection veins, is there a way to determine the original % of mush or melt? And what are the best references to consult about this? I think you're muted, Emilie.
Joanne, I'll have to look into that and get back to you. I'll make sure I save your question. Sorry, I can't answer that immediately.
Okay, no, that's fine. Can you hear me?
Yes, I can.
So my question is really, by the time we get a solid rock sample,
Right.
It's had a history of maybe multiple things happening to it. So is there a way to back out the useful parameters that you really want to know in terms of, you know, how much % mush it came from, or how much % melt was in it, or anything like that?
Those are really good questions. It's not exactly my field, but what I do know is that people do sometimes try and, you know, undo any shearing that happened to a sample, but that doesn't mean that a whole other set of history isn't taken into account. And clearly it's only it's a good step, but it's not clear it totally solves the problem.
Okay, well, thanks. Yeah, and if you can suggest any more things to look at, that would be great.
Yeah, I'll do that.
Thank you.
Christian, I did have a question for you if we don't have any others, which is this sort of concept of, I mean, all these things are very complicated, right? And people want to do different things and there are different applications. What's the practicality of building different tools that could interact with, that are accessible enough with kind of inputs and outputs, like Mark talked about, that you can put them, one of our postdocs was talking about Lego blocks, right? And so even from a data inverse problem, it's like, well, in this case, I want to do teleseismic data and some reflections. In this case, I want to, you know, do electrical conductivity. How could you, is that realistic more in the modeling world, or?
I think it is, and it should be. And it's part of the equation of trying to do upscaling right, I think. To have models that basically have inputs and outputs can communicate, not only with other models, but with other scale of models looking into similar things. And it's tricky to do. Mm-hmm. And I think that requires a very good understanding of the smaller scales that you want to look at. And then you move basically as a cascade to larger scales, understanding what you sacrifice along the way and what you're able to sacrifice, and having models that carry the information that is important for the larger scale. But not only in terms of averages, right? When we do upscaling, very often we look into averages. We don't look at distributions. You need to look into basically outcomes that are basically more on the fringes as well, to basically carry forward a sense of sensitivity that you're losing by upscaling otherwise. So we need to be very careful on how we do that. And I don't think we have a good framework to do it. But technically it should be possible. I think it's a frontier, not in our field, but in every field, I think, at this moment in physics, for example.
Great, so we have another question from Steffi Buckart, who says, thanks for the great talk, Christian. As Emilie was showing, the structure of the crust actually matters. The thermal models you showed were all balloon on string geometries, and the internal dynamic models were all big tanks. But in the field, I haven't encountered outcrops of either. What do you think the geometry and structure of shallow crustal reservoirs is neglected in modeling?
It's a very good question. It's for two reasons, I think. I might be wrong. The first one, I think, is this principle of simplifying things as much as possible. In the lack of better constraints, or if you want to look at the generic model, you start with simple geometries. And the complexity that you see, for example, in the field is probably way beyond what we can do numerically in most of those models. So then you can go back to geophysics, for example, what Emilie was showing, but then the scales that you can resolve are fairly broad too. And so very often what is done, especially at scales where we don't have those kind of geometrical constraints, at least not very well, is to really simplify it a lot. And then potentially you can just assign, let's say, a rectangular shape and change that shape to see if there's an aspect ratio dependence to your outcome. That would be one way to do it. It's not very satisfying because if you put the slope, for example, in your system and you break the symmetry with gravity, you can basically influence convection patterns or different kind of things that you could have in the system. So I agree. I think we're really at the first steps of making relatively simple push understanding a cause and a consequence in those models.
Okay, we have the next question for Chris as well from Chiara. Great talk, thanks a lot. You touched my fundamental points, many fundamental points. Do you envision any ways we will be able to overcome the great limitations we have in defining our initial and boundary conditions when we want to model something at least similar to magmatic systems?
So the problem with this answer is I'm Swiss and I tend to be not the most optimistic person in general sometimes. I don't see how, but let's see. I hope we can. You know, the problem is when you look at the frozen system and you go to the field and, for example, look at an exhumed Pluton, you get a lot of spatial information. But then you lose a sense of temporality, what it was at the right time for me and how should I look at. You have an integrated kind of temporal evolution that you have in front of you. When you look at geophysics, you have their snapshot that you want, but you don't have the right scale. It's tricky right now. And yeah, I'm sorry, I don't have a better answer.
Okay. Since there are no additional questions and we are at 1:31, I would like to thank both Chris and Emilie again for your very nice talks, as well as Philip and Mark for their talks on Tuesday, and Penny and Panabendo for moderating questions. If you do have additional questions, suggestions, comments, feedback, as I already mentioned, there is this feedback form, this asynchronous feedback form on the MCS webpage. And you're all welcome to attend tomorrow's planning meeting, which is from 12 to 2:30 Central Time. You need to register for that as well on our webpage if you haven't done so already. The purpose of tomorrow's meeting is to identify some science priorities and have a discussion about what should be a vision, what should be a modeling collaboratory like, what should it entail in order to help us achieve our science goals. And so we'll have time to talk together. We'll have some breakout sessions and more time then to circle back and talk together about this. So thank you again and hope to see you tomorrow.